Hi everyone, once again, let's continue then. Okay, that's the last part of this chapter 4, antiderivatives or anti-derivatives in American English. So again, the last 5 or 10 minutes, okay, I will send a link. So you have to sign for attendance for today. All right. So now we have studied how to find the derivative of a function. However, many problems require that we recover a function from its known derivative, from its known rate of change. For instance, we may know the velocity function of an object falling from an initial height and need to know its height at any time. Anyway, guys, as you know, I have been telling about what is it? The calculus number 1 functions. The second chapter is about limits, and the rest of the chapter is about what is it? The combination of functions and limits, right? Well, that means that the limits of, let's say, special functions. Now, chapter 3 and 4. Chapter 3 it was about differentiation, right? And chapter 4 is about application. And now for the rest of the calculus class, we'll be talking about integrals. Okay, now this is the first step to, how to say, start the learning integrals. So now in this chapter and in this section, we are going to talk about indefinite integrals. As you see in this introduction part, okay, sometimes, okay, if you are given position function, we know that if you differentiate this, we get velocity function. If you differentiate velocity function, we get acceleration function, right? But sometimes, how about if we know, let's say, the acceleration function? How can we reconstruct or restore our acceleration function? Or if we are given our acceleration function with some initial value, okay, how can we reconstruct or restore our, what is it, our position function? Actually, that is the problem of, what is it, definite integrals, okay? So anyway, let's start with this definition, because as you know in math, first we define something that okay, and after that we build other things on this definition. And using this definition, first we generate some properties, that means our tools, right? And using these tools we are making a lot of things out of these tools. Finding antiderivatives. A function f, the capital F, is an antiderivative of f on an interval I if a capital F prime of x is equal to f of x for all x in I. And also sometimes we should practice to understand the definition. Okay, a lot of times I feel that students, they read the definition but they don't understand. Okay, because definition means that we know that we have some kind of newborn concept here. Okay, so that's why we are defining this. If you differentiate a function, okay, and if you get new function, right, then we are calling that capital F, that function, the antiderivative of f. Like, for example, and we're going to see some examples here. Okay, a function f, capital F, is an antiderivative of f on an interval I if f prime of x is equal to f of x. For example, immediately, I'm going to show you more examples here. Let's say our function f of x, all right? So that's equal to x, right? So now if I ask the question, what is the antiderivative of f? I'm asking that what function's derivative gives us this x, right? So at the time, I'm just labeling this by capital F of x. So that is 1 over 2 times x squared, right? If you differentiate 1 over 2 x squared, it gives us x. So that's why this capital F is called the antiderivatives of f. Another example, like, for example, let's say g of x is equal to, let's say what we know, actually, let's say this sine of x, right? So then if I ask what is an antiderivative of g, n means that one of the antiderivatives, okay? So let me just label this by capital G of x. That means that what function's derivative is sine of x, that is minus cosine of x. Also, you can add some constant, it doesn't matter. Since they're asking us one of them, I'm just giving them the simplest one. Okay, as you see here, when I'm just saying that what function's derivative sine of x, answering this question is not always easy, because differentiating is just straightforward, right? We can differentiate every function, I mean, quite easily. But integrating functions, it's not easy. Integrating means that finding an antiderivative of a function, that is not easy. And that's why it requires a lot of practice, at least at the beginning. to actually feel comfortable about this concept, you need to practice as many questions as possible so that you can um, solve the questions fast. Find an antiderivative for each of the following functions. For the first one, for example, let's say antiderivative is capital F of x, right? Now, again, I'm asking myself, what function's derivative is 5x? So that is 5 over 2x squared. And how about the second one? Again, f of x, we have just done this, that is minus cosine of x. Now, how about this? Question C. So that is what function's derivative is 5x minus cosine of x. Actually, we know that actually this differentiation is it's a kind of transformation. Maybe later when you take linear algebra, you understand this concept better when we just say linear transformation. We are transforming one function into another function, right? By differentiating. Because differentiation is a kind of operation, right? So what functional derivative 5x we have just done here? It is 5 over 2x squared. And what function's derivative is cosine of x? That is sine of x. So sine of x, right? So the derivative of this function is 5x minus cosine of x. Okay, now theorem 6. If capital F is an antiderivative of this lowercase f on an interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is an arbitrary constant. Okay, now we are defining, okay, not only one, but the most general. The most general means that contains or that represents all the antiderivatives of the function, okay? And we are just labeling this by f of x plus c. Why is it so? The proof is quite simple because let me just write here. Why is it so? Suppose that this f of x, right? And let's say it is one of the antiderivatives is it is capital F of x. Okay. Now, if I ask another student, for example, Bunken found this one, and Sopon Law, for example, let's say if I ask what is this, he found another one, and g of x, right? And by definition, for this capital F and capital G, to be antiderivatives of this lowercase f and f, right? So this capital F prime of x must be equal to f of x, right? At the same time, and g prime of x must be equal to also f of x, right? Now, if you remember our corollary after the first derivative test, right? When the derivatives of two functions, they are equal to each other, if and only if they differ by a constant. That means that if f prime of x is equal to g prime of x, then how they are related to each other, then this f of x must be equal to g of x plus c. The c between among the antiderivative of the function, they differ by each other, only the constant. And that's why to define the most general antiderivative of f that includes all the antiderivatives, just adding c, right, some constant that represents all the antiderivatives of the function. Okay. Now let's get back to our example 2. Now in this example, it says, what is it? Let me use yellow here. Find an antiderivative of this. That satisfies. And also here we call this, what is it? Initial condition, right? Initial condition that passes through this. IC means the initial condition. So first we have to find this capital F, right? What is capital F of x? Capital F. What function's derivative is 9x squared? We know that it is 3 and x cubed, right? If you differentiate this, it is 9x squared. And so now, actual initial condition is given. That's why I need to add here C, the most general one. Which one we are talking about, I don't know. Okay, now using this condition, I'm going to find out the value of this C. So we know that actually F, when x equals -2, that is 3 times -2 cubed, and plus C, that's equal to -13, right? Now, if you solve this equation, we will get the value of C. C is equal to -13 plus 24, that's equal to 11. So now what is actually the antiderivative of this function that satisfies this condition? That is, let's say this capital F of x is equal to 3x cubed plus 11, right? We have a lot, actually. One of them is this one that satisfies the given initial condition. Now, find the general antiderivative of each of the following functions. In a similar way, we can solve these questions. For example, the first one, capital F of x, right? Again, we ask ourselves, what function's derivative is x to the power of 7? So that is 1 over 8 and x to the power of 8 and plus c, right? We are talking about the general. That's why I need to add c here. If you differentiate this function, you will get x to the power of 7. And how about this one? Before I continue, I can just write it as 3 times x to the power of minus 1 over 2. Then what is it is the general antiderivative f of x is equal to, and you will see that actually when I differentiate this, right, we subtract 1. So that's why I have to add 1 here. So that's equal to 3 times x to the power of minus 1 over 2. So it should be plus 1. When it comes to the front, it must cancel out with this expression, right? And plus c. So now if you simplify this, then it will be, what is it? Minus 1 over 2, 1 over 2. So that is 6x to the power of 1 over 2 plus c. Or you can also write this in root form, right? 6 times square root of x plus c. Now see here, if you differentiate this function, 1 over 2 comes to the front, 6 times 1 over 2 is 3, 3 times square root of 3 over square root of x plus, actually it's just 0. And how about h? Let me just write here capital H of x. What function's derivative is cosine of 3x? That is 1 over 3 sine of 3x plus c. Because if you differentiate this way, we get cosine of 3x. And how about sine of x? The general antiderivative of this function, capital I of x is equal to, what is it? It is 5 times cosine of x over 5. But it becomes minus, right? That's why I need to write here minus. So plus c. If you differentiate minus 5 times cosine of x over 5 plus c, you get sine of x over 5. As I say here, when you ask yourself, what function's derivative is this thing? It is not that easy. Maybe the simple one, it may be easy, but still, you need to practice a lot. In the future, we'll see that for the students who are going to take calculus 2. One chapter is actually, what is it, dedicated to only integration techniques. Okay, one chapter, because it's real integral is really, really big topic. And as I told you, starting from this 4.7 till the end of calculus, everything's about integrals. Okay, not everything. Maybe we have partial derivatives in chapter 14, but almost everything is about integrals. Now we have some formula we have already studied, right? If you look at these expressions, right? For example, function x of n, right? X to the power of n. So what is the antiderivative of this function? It is, see here, I'm just adding n plus 1 over n plus 1, right? X to the power of n plus 1 over n plus 1. Because how can we prove this? If you differentiate this function, I will get x to the power of n, right? That is the proof. And how about sine of kx? That is minus cosine of kx over k. Because when k comes to the front, right, the they cancel each other. And cosine of kx, it is antiderivative, or general antiderivative is sine of kx over k plus c. And secant square root of x, what function's derivative is secant square root of x? It is tangent of x, right? Tangent of x plus c. Cosecant square root of x, that is minus cotangent of x. And how about secant x tangent of x? That is secant x plus c. Or cosecant x cotangent of x, that is minus cosecant of x. And how about, what is it? Antiderivative linearity rules. Again, it's exactly like limits, right? Constant multiple rule. K times f of x. Then it is general antiderivative is k times f of x plus k times c. But k times c, again, relabeling this, I can just use c here, right? And negative rule, minus f of x. Then it is antiderivative is minus f of x. That's simple. I can just keep this minus out, right? Sum or difference rule, f of x plus g of x. If I know the general antiderivative of this f and g, and if you just add them or if you just subtract them, that means that we need to add their, what is it, antiderivatives, right? Capital F plus capital G or capital F minus capital G. Anyway, you can just have a look again. Once again, guys, you need to practice. At the beginning, you may just use this table, but this one is the most fundamental one, the basic one. So you have to know them by heart. Find the general antiderivative of this function. So here we have, again, solution. So we are looking for this capital F, right? Capital F. So that's equal to, here we have, I can just write, we have just found this, right? Here we have 1 over square root of x is equal to x to the power of 1 over 10. Guys, 1 minute break, okay? I'll be back soon. I just need to check something. I mean, do something. All right, I'm back. Sorry. So, well, antiderivative of this function, just using this rule, right? What is it? This one is x to the power of minus 1 over 2 plus 1 over minus 1 over 2 plus 1. So now if you simplify this, so here we have 1 over 2, that is 2 times square root of x, right? And minus, what function's derivative sine of minus sine of 3x, that is, what is it? Plus, and here we have 1 over 3 times cosine of 3x, right? If you differentiate immediately, so you will just get, what is it? Sine of 3x. That's why if you're really good at differentiating functions, immediately you can just see, what function derivative is this? We have to do this mentally. So I should just edit C, because we are talking about the general antiderivative of this function. Okay, now after these things, now we can actually define an indefinite integral. Okay, what we have been just doing here is it's just about the calculating indefinite integral. Now the collection, that means collection means that the set of all, right? The collection, the set of all antiderivatives of f is called the indefinite integral of f with respect to x, and is denoted by, see here, this long, what is it, stretched as f of x dx. And there's a reason why actually mathematicians use this notation. You will see this in the next chapter. The symbol we call it integral is an integral sign. The function f is the integrand of the integral, and x is the variable of integration, variable of integration. So now evaluate the following integrals means that simply, that means we need to find the most general antiderivative of these functions, right? Integrand functions, right? So that's why to evaluate the first one, for example, what is it? That's equal to, what is it, green? So the x squared plus 3x minus 7, what is it? It is 1 over 3 x cubed plus 3 over 2 x squared minus 7x plus c, right? And how about c or b? Let's continue with b. I have just done the square root of x, right? So that's equal to, we have 1 over 2. Let me just write it as x to the power of 1 over 2. So this x to the power of 1 over 2 plus 1 over 1 over 2 plus 1, right? X to the power of, here we have negative 1 over 2 plus 1 over minus 1 over 2 plus 1. Now we have the SC. Now if I just simplify this further, we have, what is it, 2, and here we have 2, actually 1 plus 2, so that's equal to 1 over 3, right? And this one is 1 over 3, and x to the power of 3 over 2, right? Plus, and this one is, here we have 1 over 2, so that is 4 times x to the power of 1 over 2. It's just square root of x, okay? And here we have plus c. And how about c? For c equals, right, what function's derivative is minus sine of t? Actually, negative 5. I can just keep it like this, right? Negative 5. And integral, here we have sine of t and dt, which is equal to negative 5. What function's derivative is sine of t? It is minus cosine, right? That's why minus minus is plus. So here we have 5 times cosine of t plus c. And how about d? 1 plus tangent square root of x, right? And again, if you just look at, what is it, our formula here, what function derivative is tangent squared? We don't have here, but we know that actually secant, right? If you look at this, secant squared, right? So first I can write this identity. What is that? That is 1 plus tangent square root of x, right? So that is equal to secant squared of x, right? So now if I substitute here, then we will have equals integral. We call this, what is it? Substitution, right? So secant square root of x dx. Now what function derivative is secant square root of x? That is tangent of x, right? And plus c. Guys, I think that's all for this chapter. We have a lot of examples, as you see here in exercise 4.7. We have 110 examples, but you should practice to do the questions fast, okay? Okay, this one first at the beginning, you may look at the paper. As you go further, you should also, your speech should get better and better, or faster and faster. Otherwise, just knowing is not enough. In life, also speed is really, really important, right? And for example, you are sending a money to somebody, right? It may reach in 1 day or 3 days or in an hour, or like in ABA in a few seconds, right? So actually, which one is better? Of course, speed, fast. Uh, guys, I'm going to send you the